Thank you, Stephanie, for bringing me here, and the whole lab for inviting me here today. Um, my name is Dorian Pustina. I currently work at the University of Pennsylvania in Philadelphia, in the United States. And in the last year and a half, my work has focused on patients with stroke and predicting lesion segmentation automatically, and predicting perhaps behavioral scores. Now, before I start, I wanted to mention my collaborators here. Mirna Schwartz, who is the PI in my lab, Branch Kostek, who is the neurologist, and my former supervisor, Brian Evans, who is the original developer of the AND software, Lyle Dungar, who is a computer scientist and has helped with machine learning, Philip Cook, who is very knowledgeable in all aspects of neuroimaging, and that's helping with that, understanding it better. And John Medaglia, who is a recent assistant professor newly acquired by the university, who will help me with the graph theory measures. Now, I remember when reading the introduction of a paper, something very interesting. It was stated that the history of neuroscience basically is the history of the tools that it's has used. So at some point, someone invented a microscope, and you suddenly could see the cells and the neurons, and some more later on, about 25 years ago, someone wrote in MRI, so we could see the brains in vivo. So essentially, I think it is true that the history of neuroscience follows tightly the history of the tools that it's been using. And this is the reason why today I'll be talking about tools that we use for neuroscience, and I'll be talking about two aspects. In the first part, I'll go rather quickly to explaining our method for automatic lesion segmentation in stroke. I'll explain how it works, the accuracy of the method, how we can compare the VLSM results, so the neurobehavioral correlations compare between manually traced lesions and predicted lesions, some cross-institutional validation, and then most of my talk, the second part, is going to be about the prediction of aphasia scores using multiple modalities. So, about lesion segmentations. Why do we need these automatic lesion segmentations, first of all? Well, we need them because when we run these studies on stroke patients, we need essentially two things: lesion maps in a large number of patients in the study. And we need a large number of patients because, as we know, the lesions caused by stroke have high spatial correlation. So you need as many patients as possible to try to distinguish better neighboring regions in the brain. Now, because we are using manual tracing to obtain these lesions, and manual tracing is time-consuming and has high interrelated variability. There was a paper that just came out a couple weeks ago, and the dice similarity, I'll explain later that if you don't know what it is, it was just 0.77. And so there is variability from one rater to another rater. Since we use manual tracing, it's difficult to get lesion maps from a large number of patients. So clearly the manual tracing procedure becomes a bottleneck in the study analysis. And the point here is that we don't want automatic lesion segmentation just because we want another fancy method, a new app or something, and we want to be lazy and just watch our phones and let the computer do the work. It's not for that. We want automatic lesion segmentation so we can streamline the studies, get faster data, and finish our projects faster. Now, we need automatic lesion segmentation, but the method that I'll be explaining to you today is not the first one we published. There are a bunch of other methods already in the literature. But one of the limitations of these methods is that the number of images on which they're tested are quite small. The second limitation is that these methods typically are produced by labs that are computer science labs. So they are tested for accuracy, but once you get a measurement of accuracy of the predicted lesion with a manual trace lesion, you don't know if when using massively these predicted lesions, you're getting into any sort of trouble or into some bias when you work only on predicted lesions. So none of these studies have effectively compared neurobehavioral correlations of manually traced lesions versus predicted lesions. So that's why with our method we set to get a larger number of patients, create and test our method on a larger number of patients, and then just do a proper comparison. So this is the sample that we used, patients that we have to create our method. 60 patients, all with chronic, left hemispheric chronic stroke around the middle cerebral artery area. And when we started, we had a single image available, a T1. And neurologists typically use only that T1 to draw the lesion. Now, from that T1, typically what does a human expert do? Well, human experts try to see if there is an asymmetry, left, right, and missing signal, or there is an area of the brain that you know that it should be there and it's not there, something like that. So that's what we try to derive from this single T1. And we computed a series of other images by, such as mathematical derivations of the T1, by applying some formula or something else to the T1, and created these 11 features, 12 together with T1. So this one, for example, is a geometry feature, is a simple 3-tissue segmentation of the brain. Another one is a radius magnitude. This is just an asymmetry measure. The asymmetry is simply taking the brain of the subject, flipping it on the other side, the x-axis, the y-axis actually, and then just subtract. And other features have to do with the deviance from a set of controls. The controls were age-matched 80 controls. Now, at this stage, which we call partially automated stage, everything is in template space. So don't forget that for a moment. We have already normalized in template space the T1 image of the subject. So the first thing to do is to understand, are all these features necessary to get a good segmentation, or maybe just some of them? So we ran a procedure like similar to a stepwise procedure by adding one by one all the features, first looking at which one is the best, then taking that one, adding another one, and trying all the possibilities, and making two, selecting the best two, then adding another one, and so on. And by running this procedure, 6 features came out as important. This is their order, the ranking order of how they were selected. And now, using these 6 features, what we do is train a machine learning model. And the way this is done is, here are the 5 features plus the T1 itself here. And we create different resolutions for each of these features. And we start with a coarse image first at 6 millimeters voxels. And we train a machine learning random forest with that by taking the samples of voxels, but not just the voxel itself, also the surrounding voxels. Why? Because when you want to predict if a voxel is lesioned or not, you also want to understand if the voxel is in the middle of a lesion. A voxel cannot be lesion on its own, by itself, a single voxel. So we get also this neighborhood information. And all this is stuck into a matrix, and a random forest model is trained to understand the relationship between the voxel values and the neighbors and the status of the voxel. Now, I'm not explaining right now what are random forests. I'll explain a little later how they work. So essentially, once we do this, we can also get prediction from this coarse resolution image at 6 millimeters. So what we do is feed it back and provide it as an additional feature to the next level, at 4 millimeters. We do the same, train another random forest model, get a prediction, feed it out, and go to the next step of 2 millimeters. So we go gradually from coarse resolution to fine resolution. Yes?
One question about the resolution. Are they somewhat tailored to the size of the lesion, or do you apply the same to order?
This is, no, it's not tailored. This is general for everyone. So 642 is just the one that we use for the study, but one could try other resolutions. As a matter of fact, one of my collaborators has noticed that if we go in a U-shaped resolution, start 1, 3, 6, 3, 1, it may be even more successful. But this is just what we tried at this level. By the way, this is the same concept that was used in another segmentation algorithm for tumor segmentation, which won the challenge in 2014. So that's why we kind of stayed there, tried to not move too much from that concept of hierarchical resolution from down up. Now, at this partially automatic stage, we have, I said, everything in template space already. And just this, at this stage, all we want to know is, can we use this model to predict lesions at all? Do these random forests predict lesions well enough? Well, the dice similarity at this level was 0.72. What is dice similarity? Is, say for example, the red part here is the true manually traced lesion, and the green is a predicted lesion. Dice similarity is this area in the middle that overlaps both, divided by the total and multiplied by 2, but it doesn't matter. And it ranges between 0 and 1. 1 is perfect when there is complete overlap. And we also ran a bit of validation by using different people to train the model and predicting the same person multiple times, 10 times. This gave us an indication how stable is the model, how stable is the prediction. And it turned out that dice similarity there was 0.94. It's very, very similar no matter who you train the model with. So essentially this part that I just talked about, this partially automated stage, just verified that this wheel here, the lesion prediction, worked. But there's this other wheel here. You need a registration to template to make this thing work. So how do you get the lesion prediction if you don't have a registration to the template? And how do you register to a template if you don't have a lesion mask first? The idea here is that because there is this circularity of the needs, we could apply a continuous loop. So first you get an initial prediction, you get that mask, you bring it back, and you apply a registration. You get a new prediction, you bring it back, apply a new registration, thus improving gradually both the registration and the prediction. So this was what I showed you before, the internal loop just for getting the prediction of the lesions. This is the other part, the full loop of the register predict portion. So this is the part we first run the full thing with an initial mask, which is taken from the asymmetry of the brain signal, and then we get, after running all these internal loops here, we get a lesion mask, we bring it back in subject space, and start to run another prediction, and so on. And we do this 3 times. Right.
So how long does it take a subject to run?
For the training is one thing, and it may take 2 or 3 hours if I remember correctly, and it needs quite some memory. It may need like 40 gigs of memory. For the prediction, it doesn't take much. It's for the prediction, it takes about an hour something. It's quite enough, but the prediction itself, so this internal loop is not what takes the time. What takes the time is the registration. Particularly the last one, which we want to be as perfect as possible. We run through registrations. So these are the final, I want just to show you a few examples. So this is someone with a large lesion And in red here you see what was drawn manually. In blue is what was predicted by the algorithm. Here's another one with a little more intermediate lesion size. Again, in red is the manual tracing, and in blue is the linear prediction. And this is someone else with a small lesion. And this is a general overview of everyone, all the subjects. So the first line is the lesion volume itself. The second one is dice overlap. And the average dice overlap for the full group was 0.70. The average displacement, how much the prediction is displaced in space from the true manually traced, is 2.54 millimeters. It's quite small. And the hazard distance is just another measure of the maximal displacement between the two. What's important here is also that the predicted lesion size is highly correlated with the true lesion size. The correlation is 0.96. And it's important because, as many of you may know, the lesion size is one of the most important predictors of aphasia scores or even neglect. Okay, so the next step was to say, okay, we have this method. If we use this method, is it can we get reliable lesion to symptom mapping from predicted lesions? So what we did is comparing VLSMs between manually traced and predicted lesions. And from an overview, you could see that we had 5 scores: comprehension, repetition, picture naming, auditory discrimination, and rhyme discrimination. And comprehension had some overlap, but it wasn't that great. The others generally were quite well overlapping. And we took 2 scores to try to understand this better. One was the peak-to-peak displacement, so we took the voxel with a maximum t-value on one side and the voxel with a maximum t-value on the other side, and we computed the distance between those. And it turned out that for these 4, that distance was under 2 centimeters. For comprehension, there was quite a distance. It was 6 centimeters because the peak was here for the predicted lesions in the posterior temporal area, but it was somewhere in the frontal area, the middle temporal gyrus, for the true manual traced lesions. The other thing that we did is just correlate the voxels with themselves. So we have 26,000 voxels, and we just correlated them. If there was a lot of displacement, the correlation would be low. And those correlation values were, again, the lowest one was comprehension, and then for the other ones was 0.73 and up.
It's interesting for that measure comprehension and naming don't differ that much.
Sorry?
Whereas, well, with the peak distance, comprehension was a lot worse than ours. With this one,
Yes.
comprehension isn't much worse than naming.
Yes.
Or
Yes.
vice versa.
Yes. That's true, because you still have to imagine that all of this area, there are areas that are pretty well overlapping. Although this is yellow, for example, it's still a high value compared to the borders.
As long as there's a linear relationship.
You know. Now, another thing that we did is, instead of using voxel-based lesion to symptom mapping, was to use regional-based linear regression. So in that case, instead of having the voxels being ones or zeros, we just compute how much damage is every region in the brain. And we use the regions from the AALS. And in that case, what we found is that this type of analysis is more robust to the error. Because always the top 2, among the top 3 regions that came out as important, there were always 2 matching between the predicted lesions and the manually traced lesions. Now, I'm going a little bit fast on this part because there's a lot more to cover. And I don't want to, I realize this is about 45 minutes, something like that. Okay. So the other thing that we did is take our model and apply it to completely new data set. Train on that data set again, always with a leave one out, just as we did with ours. But the data is completely coming from some other institution, this town, in this case, Georgetown University. And the results were very similar again. DICE was, again, 0.70. the average displacement was something around 3 millimeters. And again, there was a high correlation between predicted lesion volume and manual trace lesion volume. The final thing that we did is we said, well, if the model is good, we should be able to train the model with our data and send it out to predict someone else's data. And that's what we did. We trained the model with our 60 patients. We predicted the 44 Georgetown patients. And the dye similarity here, we expected a significant drop in dyes, large drop. But the dye similarity was quite good again, which means essentially that these trained models are capturing very well the rules used by experts in any institution to draw the lesions. Now, as a final notation, this is a table that was sent to me by someone from Northwestern University. They have another method for lesion segmentation, and they try to compare it with Linda, and in almost every subject they tried, Linda is performing as well or better than their own method. So, to summarize, Linda was tested on 105 subjects. We had one failed case for the Georgetown data set. So, but the failure case is quite low, it's less than 1%. And we investigated also the changes in these neurobehavioral inferences, so VLSM results. And we verified that there is transferable knowledge between labs. So we could train a model in one lab and send it out to be used in another lab. Is there any question about this part? Because I'm going to move to the second part, which I like a little more.
Just a comment to stick up for Emmanuel Stegmatakis' paper, even though he only reported 2 in that paper. So I was in that lab before I was here, and the same method got used in a lot of subsequent papers, so it was tested.
Which one?
Stegmatakis. It's one of the articles.
Yes. It's one of the earliest, it's 2005,
Yeah,
right?
yeah.
It's one of the earliest, and the number
just
was...
uses the T1 intensity, and that's all.
Yeah.
Very, very simple.
Very crude beginning.
I mean, for chronic left MCA and parts of language problems, it did its job.
Yeah. Well, yes.
Is there any technical reason why this wouldn't work with preclinical data, like rodent strokes?
What type of patient?
Preclinical data, like experimental stroke in rodents, rats and mice, just images with stroke lesion.
No, there
We
is
have
no
a
reason.
template and
There is no reason for that. You just need to train the model
Yeah.
to make it understand what is a lesion. I mean, the algorithm doesn't understand at all where are those values, the voxel values coming from. All it needs to know is that there is a relationship. The only thing is that you may need good sampling. So with not 1 millimeter voxels, because with a mouse brain can be pretty big and you don't have enough samples to train them on. Yeah. All right, so the second part is something that I've been working on the last few months. And it has to do with predicting aphasia scores this time, not just lesions anymore. And the idea behind this project is that we need to move away from these null hypothesis linear models. Why is that? Well, first of all, I think we're using null hypothesis linear models in the wrong way in many directions. First of all, these null hypothesis models are built to test one hypothesis, not 100,000 or 1 million, as we are doing today with brains. The second part is that we know that the brain is a connectome, and there are non-linearities between the status of a region and the behavior of a patient. Who guarantees that the relationship should be linear? Most of the things in this world are not linear. Plus, because the brain is a connectome, regions of the brain interact with each other. So we are not going to get, the chances of getting non-linear relationships are pretty high. And this up here is just an example of, from the theory of chaos, of how this double pendulum creates complex non-linearities that are very difficult to predict. And if they can get something like this with the double pendulum, what can we get in the brain when there are hundreds of regions if we just do a normal parcellation these days are done. Now, sometimes people that use linear models say, you know what, we can still model interactions between brain regions by adding interaction terms. But if you add interaction terms, you end up severely restricting the number of variables that you can use. From my calculations, if you have 4 variables, you can already saturate 100 subjects with a classical rule of 7 subjects to 1 variable, because combining all the interactions between the 4 variables completely brings you to the limit. Now, sometimes people say, okay, I can still model nonlinearity by adding a cubic term or a quadratic term. Well, that is one type of nonlinearity. It's not, nothing guarantees that the nonlinear shape between the relationship between the behavior and the status of a brain region will follow that type of nonlinearity. It may be another shape, like sinusoid or something like that. And the final thing that I wanted to mention is that there is still being used the concept of statistical significance as a proxy for predictivity, how good this can be a predictor to the outcome. Well, statistical significance is not necessarily a good predictivity measure. And there was also this recent paper from Lowe in PNAS where they explain why statistical significance should not be considered the best measure for predictive power of a variable. So essentially the question is, nowadays we have a lot of data. We could have lesion data, we could have DTI, we could have resting state. We could use graph theory measures and different types of measure. And for each measure we could take over 200 regions in the brain. So we have massive data. How can we use all these data together within a nonlinear framework to achieve some predictability of aphasia scores? Well, the answer that I've tried to give myself is, well, why don't we use random forest models, which are very good at finding nonlinear relationships, at finding interactions between variables, and use these random forests separately for each measure, for example, for DTI, for resting state, for lesions. Get preliminary predictions from each of those, and then blend these preliminary predictions together into a final prediction. It's a concept that brought one of the a group to win the Netflix challenge a few years back. Netflix decided to offer $1 million to whoever will achieve an increase in the predictability of the movies that people would like. And the people that won the challenge took a series of methods, applied preliminary predictions from all those methods, and then took these predictions at the next level by combining them. So we are using random forests. How do random forests work? Random forests are very simple in nature. At the risk of touching a delicate point here, I may make some political analogies here. So, say for example you have two variables, variable 1 and variable 2, and you want to classify people based on those two variables, in the green and the blue. What random forests do is start to make very sharp decision. If variable 2 is lower than this value here, then it's green. If it's higher, then it's blue. So at the next level you have the first line, then you go to the next point. Now, if this variable is lower than this value, and this value, and the first variable, is higher than 2, then it's green. But if it's lower than this value and lower than 2 in variable 1, then it's blue. You understand the concept? Very, very simple. if migrants are taking our jobs, we build a wall. So this can keep going on all the time until a relationship is found. And then the interaction between variables can come out naturally. This is just another explanation with the blue and the red dots. And you can see here how this is an if and if then else statement. If you ever did some programming, if then else. If this is bigger, then it's and the second variable is smaller, then it's blue and stuff like that. What I showed you here is classification. The concept of regression with random forest is very similar in nature. You first cut a line here. Let's say this is the variable, the input variable. This is the output variable, the y. You first cut a line here and you say, well, if this input variable is higher than the value here, then the output variable must have this value here. If it's smaller, the output variable will be something like here. Then you could still keep going by adding more levels of complexity with if then else, right? So in the second part here, the prediction follow a lot more the shape of the data. And by the way, this is an example of data that are not following a quadratic term or a cubic term, but maybe complex. Now these are simple trees, decision trees. How do we go from a regression or decision tree to a forest? The idea is very simple. Instead of presenting all the data to a bunch of trees, from which you would get the same results because you're presenting the same data and the same variables, you sub-select a bunch of subjects and a bunch of variables, and you just show that to a single tree. And at the next decision point, you show another bunch of variables, and so on. The idea here is that each tree is going to be a weak learner. But together, these trees come to form a strong learner. So if there is some generic relationship between variables and the outcome, it will be understood better by the random forest model. So why are we selecting random forest anyway? Well, here's an example. Here's the problem of the exclusive OR. Say, for example, you have two variables, variable 1, variable 2, the Wernicke area and the Broca area, just as an example. If both are lesion, maybe the right hemisphere takes over. And the outcome is still good. If one of them is lesion, maybe they just add noise to the computations, so the outcome is bad. And if they are both okay, the outcome is still good. Now, if you try to model this with a linear model, it will completely fail. But random forest will pick this up very easily. Here's another example of an interaction between two variables. Again, the linear model here have difficulties to pick up the relationship. Random forests are much more similar to the true example. These are simulated data, but it's just to make a point. And here's another example. This is a V-shaped or U-shaped relationship between an input variable and an output variable. Now, if you try to model this with a linear model, it will be very, very difficult. It's impossible to get any sensitive result. But with random forest, you kind of get the same nonlinear relationship. So essentially, random forests are good because they can find these multivariate relationships, they can find nonlinear relationships, and they have other strengths because they are robust to outliers, and they have much less overfitting because the model, the data is never shown all together to a single tree. Each tree sees a subset of subjects, a subset of variables.
What's
Yes.
the minimum number of patients you need to run that analysis? You need quite a lot.
I've tried, one of the processes I've done HBM is with 18 patients, and I've been doing that also with 14. So it's not, it may be, if the question, the difference is that random forest introduces some noise to the prediction. So if you have a variable that is perfectly linear and perfectly correlated, you're better off with a linear model. But if your variable is complex, has multiple predictors for the outcome, then random forests have the advantage and are a little more stable. It has also some limitations though, because random forests are limited to the data range that you show to it. So if your patient stop a WAP score at 80, random forest cannot predict above 80. You cannot tell random forest an egg costs $2, 2 eggs cost $4, how many cost 10 eggs? It will tell you just the last number that it saw. It cannot go beyond the data range. As I mentioned, you can introduce noise, and sometimes it's called a black box because the relationships can be nonlinear and complex inside, and the variables can interact with each other, but you don't know exactly this interaction. It can be, there are hundreds of trees, so you cannot go to one of them and say, yeah, this is the relationship between the input variables and the output variable. So random forests though have an interesting output, which is called variable importance. So what this variable importance does is, if you have 100 variables and 50 subjects, it takes those each of those 100 variables and it permutes them and computes the difference between the correct order and the permuted order on the out-of-bag data. So on the patients that were not presented to the model. So it offers a huge advantage because it is inherently cross-validated, and it's very useful to understand what are the good predictors. Now, what I'll be using is recursive feature elimination using random forest. This is very similar in a sense to backward elimination of the variables. If you ever saw that with the linear models. The idea is to build a model with all the variables, rank the importance of the variables, and eliminate the last 3. Then you do it again and eliminate the next 3. So if you have 200 variables, you can start to prune 3 by 3 until you find an optimal level of variable number that you need. This is done with a carrot package. This is done multiple times with a 10-fold validation, repeated 10 times essentially. And to understand the correct number of variables that you need as you eliminate, you compute the root mean square error, so the prediction error of the fold that was not used inside this loop. And so finally, just order all the steps, all the numbers of variables, and you just select the one that has the least root mean square error, the least prediction error. Okay, so now let me switch to the data, which is a little more interesting. This time that we have 53 patients, not the same 60 as before. And this is the average lesion map of those patients. I've included everyone here, so there is no thresholding. If we threshold it the way we do with VLSM, with the 10% rule, the area would be just this one in the middle. And I'll be showing here some results with VLSM. Those are obtained only from this area here. So the idea that I advanced before is, how about if we take individual predictions from DTI, from lesions, from resting state, and we blend them into a final model. This is called prediction stacking or prediction blending. And I'll be using all the time this atlas of reference from this Nature 2015 paper with 268 nodes. I'll be using this atlas both to compute damages, regional damages, or to compute graph theory measures. So which graph theory measures? There are 4 graph theory measures. Are you familiar at all with graph theory a little bit? So graph theory is like considering the brain a network. and the nodes in the brain communicating with each other. And there are some measures that define values for each node. One of these measures is degree. So the number of connections that that node have with the other nodes in the brain. A second one is betweenness centrality. Betweenness centrality, let me switch to the plain English version, it tells us how much is on the way, how much this node is on the way of signal flow between nodes. Another one is local transitivity, sometimes called clustering coefficients. It's how much this node is in the middle of a cluster of other nodes that are connected to each other. And finally, local efficiency is, it shows us how well the signal flows within this cluster. I'm making it very plain English, pardon if there are imprecisions on this graph theory. This is just pre-processing of resting state data. I just wanted to show the steps that we did and how we followed all the images from their first point to the other points. This is where the lesion is. This is the segmentation in different tissue types. The parcellation maps. This is the final connectome matrix. The black lines are where the lesion is. So this was just for quality control, basically. And this is on the resting state side. There is a DTI side. Actually, DTI, I'll be talking all the time about DTI, but I'm fully aware that DTI is not the correct term here. We are far from the tensor concept. I don't even like the tensor concept anymore. So essentially what we did with DTI is take one brain atlas that is available online, the IIT atlas built from 72 subjects, built a full brain connectome tractography from that using MR-Trix and the anatomically constrained tractography algorithm. And then after building 70 million fibers with that, we started to reduce the fibers to 10 million using the SIFT algorithm. Maybe some of you are familiar with that. And once we have this final full connectome from the atlas, what we did is lesion the tracks, the lesion the streamlines, eliminate those that pass through the lesion. And finally just get the same measures, the same graph theory measures, degree, betweenness, and the other stuff. So there are already, you can understand there are already, we have 4 graph theory measures with resting state, 4 with DTI. Each of them has 268 nodes. So there's a lot of data, a lot of possible predictors. And there are 4 behavioral measures that I tried. If I have time, I'll go through these other 3, but essentially at this stage, I just wanted to show you the example of one of them. These are 72 regions in the brain that show some kind of lesion. And the idea here is, with that recursive feature elimination, out of these 72 regions, find out always which are the best predictors of that aphasia score. This aphasia score, by the way, is PNT, is Philadelphia naming test. It's just picture name, to make it simple. All right. Now, this is the first example. So these are the regions that for naming came out as important. Now, the method is kind of new here, random forest, recursive feature elimination. There's a lot of new things. So at some point I started to think, how do I know that these results are real? You know, we don't have ground truth data, but we could run a VLSM. VLSM is just doing voxel by voxel, but maybe a rough overlap in space could be a good indication. As a matter of fact, if you check the VLSM map, it has a high spatial correspondence. And using these areas here, we could do always a k-fold validation, prediction of the results, which is shown here, of the PNT values, with a correlation of 0.57. Now, the next part has to do with graph theory measures. And if you've never seen that, graph theory measures depends on the thresholding of this brain connectome. The thresholding is an important factor. Normally people just do thresholding at one level. Typically they check a range of thresholds. You leave 100% of the connections in the brain, you leave the top 10%, you leave the top 20%, and they typically select one of these thresholds. We try to see what's going on at different thresholds. We notice that a single threshold is probably not going to be good enough. This is DTI here, and this is resting state here. If we stay always at the same level, for example, this is one of the highest points here. 1, 2, 3, 4. Let me go back here. So this is one of the lowest points here. It can be one of the highest points here. So a single threshold may not do it. So what we did is use different thresholds for degree, for betweenness, whatever was the best threshold for that specific measure. And the same thing was for resting state. And even for resting state, there's the same story. You can see that at full no thresholding resolution, at number 1 here, the value is very low, but for betweenness, the prediction is still very good. Yes?
Sorry, I didn't follow what the 2 different lines were, the red line and the
The red line is with some feature elimination. So you don't use all 268 regions, but you only use a subset of those that you select. The black line, and I didn't stop to explain this enough, shows all 268 regions. Typically the prediction is good with a selection of the regions, not when using all the brain. And these small asterisks here, they show the significance between the full and the selected predictors. All right, so now I explained also these graph theory measures. What's going on with DTI? For naming, there are only 2 regions that came out as important. They are both subcortical, in the cerebellum, the brainstem, and using only those two regions, I could predict with some cross-validation at a correlation of 0.64. Now, I'll be going on a little faster now, without trying to explain what each of these areas mean. This is betweenness. So how important is a node for information crossing into it? And there are 13 regions here we could predict with a correlation of 0.67. This is local transitivity or cluster. And the correlation here was 0.79. These are 11 regions from efficiency. So how well the signal travels in these clusters. And the prediction is 0.64. Now this is just an overview of the nodes in the brain. With red are those that will be lesion to some degree. And here are the connections that are important. These are 160 connections that were important out of 12,000 connections in the brain that could have some kind of damage. And using these 160 connections and our 53 subjects with a K correlation, the correlation that we could get was 0.72. Switching to resting state. There are 2 regions for resting state degree. Using those 2 regions, the correlation is 0.48. There are 14 regions for betweenness. The correlation there says to be 0.6, but it's not following the diagonal line, as you see. Local transitivity, the correlation is 0.57. And finally, efficiency, the correlation is 0.38. Now, this is the same thing as before. There are 800 connections that seem to be important for predicting naming out of 35,000. Again, with these numbers, if we use linear modeling, we would overfit badly. Now, we have all these predictions, these little predictions, the DTI ones on the top, the resting state here, the one from lesional information here, and I also introduced lesion size. So we have 12 preliminary predictions. If we combine those in a final random forest model, we go up to 80.83 of correlation. And if we plot a little bit the variance that we will get if we repeated this time multiple, if we repeated all the procedure multiple times, we would get a graph like this. The 12 predictors are from here to here. These are the box plots of the range of the correlations that we would get. Now, alone, each of these would be around here. If combined, it's in the all together, all 12 together is the red box here. If we run another feature elimination at this level, because maybe not all 12 are good for prediction, only these 4 would be selected. And using these 4, the prediction would go further up, around here. Now the same story would apply to the other, okay, just checking the time, last 2 minutes. So I'll just skip showing you the figures and just show you this final plot. This is for WebIQ, generic aphasia quotient. And again here, the top predictors would be up here. But if we combine those into a final model, the final prediction is much higher. It's improved. This was the generic WebIQ, generic score. This is a repetition. The 12 scores and the full 12 and the selected 4 here on the side. Now notice also one thing. Damage is frequently not one of the most important ones. DTI frequently gives better predictions. And this is, I'll show this a bit later. Let me show you the last prediction is for comprehension. The 12 ones, combined 12, and only these 8 on the right. What is this? All of this telling us? Well, first of all, these random forests can resolve most of the limitations that I mentioned at the beginning. They can provide they can detect nonlinear relationships and interactions between variables, and they can also provide a powerful tool in our imaging, which I think we should consider more carefully. And this prediction stacking is further improving the advantage that random forests give. And there is evidence from law that the most correlated predictors are not necessarily the most predictive ones. Let me go back to these selections. Now if you see, this is not selected, for example, here. It's selected this one, down here. Because this may provide more information beyond what is already provided by other ones. And to go back, the final point that I want to make is that the disconnection of tractography, the disconnection of brain region might be more informative to predict aphasia scores than simple lesions. And this is a point that was made also about 2 weeks ago in a new paper from New York group that just compared lesions and DTI disconnections. So this is all I had for now. I went a little bit over time, but I hope it was informative to some degree. All right, thank you.